And then we're going to use that. We're going to do some fun stuff in 6.3 looking at ecological, biological models, okay, of interrelated populations. Any questions? All right, let's do it. All right. So we're going to be starting again with 6.2 and finishing that up. So we talked about how to characterize the critical points of a system, of a linear system, right? So if we got nice linear coefficients in that matrix, coefficient matrix, then we can categorize the equilibrium points. Find the critical points of the system and look at the signs and the values of the eigenvalues. Okay. All right. We even looked at if we had a non-homogeneous system. If I didn't have 0, 0, if we found another point, how to basically shift the whole system so that that critical point is centered in 0, 0. We shifted it to what we call the UV plane, just by making an appropriate linear shift in x and y, transforms the system into one that has a critical point at 0, 0. Find the eigenvalues of the coefficient matrix and characterize that critical point. Okay. So we're going to go one step further today. We'll try.
Everybody, let's try.
Yeah.
Okay. All right, there we go. So more section 6.2. So today we are going to start with the system dx dt and some function of potentially both variables x and y, right? And remember, t is the independent variable, and x and y are the dependent. So a function of this form that involves only x and y, this system will be what we call autonomous. Okay? It does not involve the independent variable t. And dy dt equals some other expression, some other function of potentially both x and y. All right. So now in this case, we're going to consider the situation if f and g are not quite linear functions. And when we say linear, in the dependent variables x and y. All right. So in this case, that these functions are not necessarily of the form ax plus by, okay, constant coefficients in front of them. We could have x squared or x cubed, or a product term xy, right, which would not be linear, it would be a degree 2 term. All right, so assume somehow we can still, if we are able to find a critical point, or same thing, an equilibrium point of the system. Say x naught, y naught. By some means, we're able to find a critical point of the system. we saw that last time about this shifting business. I can shift this somewhat by introducing this substitution. Say u is equal to x minus x naught, and v is y minus y naught. So that would be a linear shift. That still doesn't make the equations linear, but what it does is it centers the critical point. To 0, 0 in what I'm calling the UV plane. Okay, so it carries that, it's a transformation. Now I'm going to, a little bit of calculus here. So this is a little bit of aside. All right, now I'm trying to give you some of what the book talks about. It goes into detail about this. I'm trying to break it down, not so much detail, but also so it makes sense as far as why we can do this. In Calc 4, how many people, I want to just a break, show of hands, how many people have taken or are currently taking Calc 4? Are currently or have? Most of the class. Okay. So remember, if you have a nonlinear function, right, and it's in x and y, a function of x and y, its graph would represent a surface. Okay? And if it's not linear, then it's not a plane. A plane is a linear function of x and y. If it's not linear, we can find a linearization of that surface at a particular point. Yeah? That's, in essence, the equation of its tangent plane. The tangent plane. So we can linearize this system, well, f and g. So linearization of a function f near a point x naught, y naught. Now, of course, we let u equal x minus x naught and v equals y minus y naught. So the linearization of this, we call this L or whatever, but the linearization means, okay, so if a point away from that center, x naught, y naught of linearization, if x, y is near that point, then the linearization, I could say that f of x, y is approximately equal to its linearization. The linearization at this point, if you recall, is the value of the function at that point plus, and this is where we have to recall partial derivatives. The partial of f with respect to x, evaluated at x naught, y naught, times x minus x naught, right? Plus the partial with respect to y, evaluated at x naught, y naught at that point, times y minus y naught. Okay. All right. Oh, and this, that's u. This, that's v. So u and v just represent some distance from x and x naught in this linearization. The distance between the x coordinate of the critical point and the value x that we're dealing with. All right. So, and x naught, if we rewrote this, we could write x naught as, well, we don't want to do that. We're just going to leave it as x naught, y naught, plus times u, plus f sub y, x naught, y naught, times v. Okay? But what we can do over here, that x and y, if I rearrange this, this is f and x would be u plus x naught. So some small distance away from that critical point x naught would be right here. So x naught plus u and y naught plus v. Can be approximated closely by this. There is technically some error term. I'll use epsilon involving x, or u and v or whatever. there's technically some error term that goes to 0 the closer that x and y is to x naught and y naught. In other words, as u and v go to 0. Okay? We're going to disregard this. The book discusses this business, but it's a very good approximation as u and v approach 0, okay, to this linearization. Okay? And one other note, if you just walked in, where f sub x refers to partial derivative with respect to x. So partial derivative of the function f, but with respect to the variable x. Okay? So this business, right, that's the tangent plane exactly. So another way of writing this is just the partial derivative with respect to the variable x of the function f of xy. So partial derivative, you've probably seen it before. If you're taking Calc 4 now, if you saw it last time, partial. Okay? And we'll talk about how we find them, a little bit of review about how to find partial derivative. Partial with respect to y, same definition. Okay? So partial of a function with respect to the variable y would be that. Okay? Treating y as the variable and everything else as constant. Okay. So that's the little aside. Now, one thing to note with this transformation, this is a rigid transformation. So du dt equals, if I differentiate the right side with respect to t, I just get dx dt. And dv dt is also just equal to dy dt. Okay? So it's a linear shift. The derivatives stay the same. They're equivalent. All right, so our system becomes, call it 1. I can replace the dx dt with du dt. So we got du dt equals, and f of xy, I'm going to replace f of xy with its very close approximation, this guy. Okay? Very close approximation. As u and v approach 0, of course, then I get just a true statement. Oh, wait. Yeah. Anyway. Notation both. So I'm going to replace f of xy with its approximation. I should write technically approximate, but we got f of x naught y naught plus partial of f with respect to x, x naught y naught times u, right? Plus partial with respect to y at that point, x naught y naught times v. Okay, and similarly, dy dt can be replaced with dv dt. What we're doing is we're transforming this system into one involving u and v, like we did last time. Except it takes a little bit more work. It's going to involve partial derivatives. And here we got, this is the function g now we're dealing with. So g evaluated at x naught y naught plus partial of it with respect to x at that critical point times u plus partial of y at that critical point times v. Okay. Now, one other thing. We are working on this assumption that we know somehow we're able to find an equilibrium point, x naught, y naught. And the definition of an equilibrium point is what? Right. In other words, if I plug x naught, y naught into, it makes dx dt 0 and dy dt 0. In other words, f of x naught, y naught is 0, g of x naught, y naught is 0. It's the point that makes both of those expressions equal to 0. And look at down here. This is equal to 0 since x naught, y naught is a critical point. Yeah? And so is this one. This is also equal to 0. Okay? So, finally, our system looks like du dt equals, or roughly equals, we're neglecting the tiny little error term that vanishes, goes to 0. We got fx evaluated x naught y naught times u plus f sub y x naught y naught evaluated at v, and dv dt. That term goes away, so we get partial of g with respect to x, x naught y naught times u, plus partial of g with respect to y times v. Okay. All right, that was fun. Now, this looks like, this is just a converted system into a UV coordinate system. Okay, the book goes into a lot of detail about what that represents and graphically and all that stuff. Don't care. We are going to use the results. All right. So look at the form of this system, that last one that's written up there. This could be written in matrix form, right?
Yep.
Yeah, we got something times u plus something else times v, something times u plus something else times v. This could be written, and using the notation u prime and v prime, I got u prime, v prime as a vector here, equals, and how could I write this as a matrix product?
You have to treat the whole partial derivative of x is x naught y naught as the coefficient of a.
Yeah.
Yes. It's going to be f sub x, x naught y naught, f sub y, and this is not a plus or anything, this is a space, these are entries. F sub y, x naught y
It's
naught,
a positive value, or it's positive.
g of x naught y naught, and g of y, x naught y naught. Alright, and that's a matrix of partial derivatives times uv. Now, when we find them, it's gonna be numbers because we're gonna evaluate it at the critical point we found. So it is gonna resolve into a matrix of just real numbers. Okay, this is evaluated at the critical point x naught y naught. This matrix is has a special name. This is called the Jacobian matrix. All right, we'll write it in a second. But one thing to note, though, is that once I evaluate these partial derivatives at a critical point, I got numbers here, right? And this is going to be linear in both in u and v. So u and v, when we transform it, 0, 0 is the critical point. We've taken x naught, y naught, and it's been transformed by a rigid transformation that puts that critical point at 0, 0 in this plane, UV plane. So this system has as its critical point 0, 0. Transformed. Okay. We define the Jacobian. So the Jacobian of the functions f and g. So it is a matrix. X, y equals, so partial of f with respect to x, evaluated at the point x, y, partial of f with respect to y at the point x, y. And then g, these are, you can think of them as row vectors. So f goes in the first row, partial with respect to x, then partial with respect to y. The second row is g, first differentiated with respect to x, and then differentiated with respect to y. So that matrix is what we call the Jacobian. Similar to one that you saw if you did the max and min test in Calc 4, where you look at the determinant of a matrix of partials, except it's second partials. Function with respect to xx, xy, then yx, yy. Determinant of that. All right. So this equation in 2 is what we call our linearized system. And it can be written concisely in terms of the Jacobian. So if I call uv just the vector u, then that's u prime equals Jacobian matrix. And I'm trying to bold this because it's a matrix quantity. Jacobian matrix evaluated at x naught, y naught times the vector u. Okay, so that's what we call a linearized system. There is some criterion for what makes it linear enough to use this method, because we are gonna categorize the critical points after we transform it and see if they match up with the critical points of the original nonlinear system. Okay, so there are some criterion for which, you know, this is acceptable, they're close enough, and it's, you know, they call it an almost linear system, right? It's linear enough. All right.
Divergence point for linearization.
What's that?
Is there like a line where you draw like an arbitrary line or something is more linear than this?
They go into some detail in the book about what it means, and I did some searching on the web and tried to find some other more understandable business. But once we do this, we then examine the associated critical point 0, 0. So the original critical point, x naught, y naught, gets carried to 0, 0. We examine it, that critical point, in the new linearized system. Okay? And hopefully it corresponds to the type of critical points of the original system. Okay. So there is a theorem, and this is just FYI. If we let, and there's the terminology, the notation gets to be a beast. If I let h, this vector h, just represent the two functions, f of xy and g of xy in our original system, okay? It was x prime, y prime were those. Okay? So if I just take those functions, and this is a vector function, just f of xy, then there is a theorem that tells when a system is almost linear. If that vector function h is, I'll write it like that, why not, is continuously differentiable. That means the derivatives, partial derivatives of both f and g exist, okay, and are continuous, I believe. That's the criterion. All right, so if they're continuously differentiable and the Jacobian matrix evaluated at that at the critical point is invertible. Then the original system is almost linear. And I'm going to put it this way, the original system was x prime equals f of xy, g of xy. So x prime equals this vector function h is almost linear. Because this is a definition, it doesn't just mean, it's almost linear. That is an actual thing, an almost linear system.
But it's not linear.
No, not linear, but these are the conditions that says it's linear enough so that the critical points of this linearized system correspond in type to the critical points of the original system.
What do you mean by
Invertible?
Invertible, yeah.
Oh, invertible.
Is that relating to the inverse of the matrix?
Inverse matrix, yes. Invertible means the inverse exists like a function.
Basically, it's not going to be a 0 on top. Is that what it's saying, or how would it not be invertible?
If you end up with a matrix that is non-invertible, it means that its inverse doesn't exist. The inverse of a matrix, square matrix, does not exist if its determinant is 0.
Oh, okay.
So this matrix is invertible. I'm going to do shorthand. If and only if its determinant is not 0. Does not equal 0. If it's 0, it's what's called a singular matrix. It's not invertible. Okay. All right, so that business out of the way. That's technically what one way of proving that a system is almost linear. Okay, and in the problems that we're going to be doing, they give us nice polynomial functions for f and g, which are going to be continuous. They're going to be differentiable with respect to both x and y. So continuously differentiable. And we should be able to find out if the Jacobian matrix is invertible because we're going to be looking at the eigenvalues. All right, so let's do an example. This is one out of the book, number 19, on page 395. All right. So say we got this system, dx dt equals x minus 3y plus 2xy. And dy dt is equal to 4x minus 6y minus xy. Okay. So right off the bat, I mean, this is nonlinear because of these terms right here, the xy terms. If those weren't there, then that would already be linear, and we could just move to the matrix of coefficients, examine its eigenvalues, right? And we have a nice chart. So I'm not going to ask you, I'll never ask you to have, won't have to have those charts memorized about what type of critical point instability you'll have. Okay? But one of these guys, well, this system does have 0, 0 as a critical point.
How can you know? Just because if you cover up the nonlinear term.
Right. In this one, since every term involves x and y, you notice it just disappears when I plug in 0, 0. So dx dt equals 0, dy dt equals 0.
Gotcha. So we know that if it's 0,
In
0.
general, right, that's not the case. There could be a constant at the end, stuff like that.
Sure.
But in this case, 0, 0 is already. So I don't have to worry about shifting it, but it's not linear. So I can't come up with a matrix of coefficients, a square matrix of coefficients. 1, -3, 2, 4, -6, -1, all those nonlinear terms. Just for terminology, this is our f of xy. This second expression on the right is our g of xy. We need the Jacobian matrix.